Greetings, groovy geographers, and welcome to this demo on Earth-Sun relations. So our little blue globe in space is doing two movements simultaneously. It is rotating on its axis, and it takes 24 hours for it to make a full rotation around its axis. It's also revolving around the sun, and it takes a full 365 days for it to revolve completely around the sun. So these two movements happening at the same time is going to have a lot to do with how solar energy comes into our planet and impacts different systems. The majority of processes happening on our planet, and definitely everything involving plants and animals and weather, are all, number one, dependent on where is my energy coming from. We basically have a giant nuclear reactor in the sky, that is the sun, and how that light comes into our Earth sets the stage for where we see rainforests and hurricanes versus glaciers. All right, so here's an easy demo you can do at home. If you have a globe, awesome. If not, you can even just use like a basketball, a baseball, a beach ball, your hand if you wanted to, and then some sort of a light source, okay? So I'm using my cell phone, right? You might have like a flashlight as well at home. And so if you have a light on your flashlight, think of that as the sun, right? So here's my light source. We're gonna go ahead and we're gonna focus our light source on our equator. Right? And I know the lighting in my dining room isn't really ideal for this experiment, but we're going to make it work. So you can kind of see a little bit on the video here where my light is focusing on the Earth. Okay, so as I spin around my globe, it's an old globe, so it's gonna wobble a bit. right? So my sun is staying stationary from our point of view, right? And it's the Earth that's then moving. For now, we're going to go ahead and just ignore that revolution around the Earth and just focus on the rotating, okay? So if I look at where this light is coming in, you can see that it's really focused here on the equator. So much so that you actually can see like this white spot, right? So the concentration of light coming is really focused right here. And that's the same how it is in space as well. Our sun focuses its energy along the equator, that area called the tropics. So you're going to have high quality sunlight coming here as well. But what about the rest of the world, right? So I'm recording this in the San Francisco Bay Area. I am nowhere near the equator, but I still have sunlight, right? So how does that work? Well, think about my hand, right? So right here on the equator, it's being hit full force, right? But if I move my hand to here, it's still being hit by the light. It's just at a less concentration. It's less intense, right? If I were to put my hand up here, up in Greenland, right, it's still getting hit by some sun. I can see a shadow being cast on my globe, but it's still at a lower intensity. It's less quality. And that's very much how the sun works as well. So Greenland still gets sun sometimes, but it's a lot less quality, lower quality. And that's all of it to do with the angle, right? So my sun is coming in at a direct angle right here on the equator. And where we see that concentration energy, we call that the subsolar point or the declination, depending on your textbook. Different textbooks call it different things. It's the same thing. It means where on the globe, what latitude is the sun directly overhead, right? So again, here in the San Francisco Bay Area, I might have my sun, tilted like this, but I'm not going to literally have it above my head. This doesn't happen here. Okay, where that happens is between two important lines. And depending on if you have a map or a globe, or if you go online and look at some maps online, it's often noted with a dotted line. That's going to be 23.5 degrees north, which is the Tropic of Cancer, and 23.5 south was the Tropic of Capricorn. Okay, this space in here is where the sun will be focused overhead. Okay, so that means we're going to have high quality sunlight coming in here, which means we have the bulk of the world's rainforest is going to be along the span through here. We have a lot of hurricanes through here, very warm oceans, because you have high quality sunlight coming in. But now let's think about, I got poor Antarctica down here, right? Even though my finger right here at the bottom, you can't quite tell because of the angle of the camera, right? So right now, my finger is still getting some light, right? My finger is still getting some light, but because of the angle, we call it an oblique angle, the oblique rays have to travel a lot farther, right? To get to that point. And it's at this weird kind of angle. It's kind of like if you're giving a friend a high five and you have that like really satisfying, you know, resounding clap versus if you have that like, oh, too slow and you miss, and you're like, ugh. That's kind of what's happening here. You have a nice high five happening here, high quality energy. Right here, it's like this is kind of skimming it, and you're not getting as much energy, which is why we have no rainforest happening here. And it's very, very cold, right? Same happening at the North Pole as well. Okay, so that's just kind of looking at the quality of energy. Now let's think about seasons. Okay, so we know that daylight is going to happen when I have, so my hand here is getting full on hit with light. My hand over here is not getting any at all. If I were to put an X marks the spot on, let's see, if I were to do it on Nigeria, right? If I were to, because Nigeria is pretty close to the equator, if I were to follow Nigeria throughout the whole time that it's exposed to light, that would be the equivalent of like when that location is being hit by sunlight. Okay, and again, Nigeria is very close to the equator, so it's going to have much longer days with high quality sun. Okay, so this whole space in here where it's being hit by the light, we call that the circle of illumination. And in fact, if I were to cut my globe in half, it's from Goodwill, it's fine. Right? If I were to cut my globe in half or draw with a marker, the points at which my light extends, it would make a perfect circle cutting half of the globe in light and half the globe in not light or dark, which corresponds to our days, right? Half of the earth is going to be in sun and half the earth is going to be in night, okay? So again, if you think about Nigeria, close to the equator is going to have this very long day with high quality sun, right? Versus if I do Iceland, right, up here at the top. So let's see, I think just about there is where my Iceland finally gets some sun. Oh, not anymore, right? Iceland tends to have much shorter days, right? During the winter, because it's just not in that circle of illumination as long. And again, that circle of illumination just kind of cuts the globe in half. And it's as we're watching things move through the sphere of my sun staying stationary, that circle of illumination comes down even, and it's the earth that's moving kind of dictates who's in day and who's in night. So that covers our rotation. What about the revolving part, right? I'm not going to get up and dance around my kitchen, all right? We're going to kind of just like have the earth move in place a little bit, right? But there's a reason why your globe is tilted. It's not just because the geographers, you know, made a mess and knocked things over. It's actually intentional. The earth in space is actually tilted at 23.5 degrees, which is the same number of 23.5 degrees north for my topic of Cancer and 23.5 degrees south for my topic of Capricorn. Do you think that's a coincidence? Right? So we have this angle of 23.5 degrees. So our earth is tilted. Now, if I think about, again, my sun staying stationary, I'll kind of put it like that. Again, you can see that white spot where my sun is focused. So you can see here's my line of the equator. That white spot is focused beneath my spot, the white spot, right? So right now, my sun is focused below the equator. That's interesting, all right? So right now, to move the space, okay, so I've got Brazil is getting lots of sun right there. Let's go through here. We've got a lot of Pacific Islands, right? Parts of Indonesia, Malaysia, right? Parts of Sub-Saharan Africa. We're going to be getting that nice high quality sun, right? In the southern hemisphere. And even my hand down here in Antarctica, right? If I were to have my finger here in Antarctica spinning around, my finger never leaves the light. Right? My hand here, if I keep my hand on Antarctica, that's a tongue twister, on Antarctica, right? And keep twisting it, my finger never leaves light. It's always exposed to light. What we see when the earth is tilted away from the sun, see my tilt pointing away from the sun, Antarctica experiences 24 hours of light. It's not warm. Antarctica is not warm. The penguins are still cold, right? Because that angle, that quality is still really low. So it's having constant light, but it's low quality light, okay? Now let's go ahead and flip it around. So now we have the earth is angled towards the sun, okay? So once again, my finger here is at Antarctica, and I can spin the globe, but you can see my hand is never getting exposed to any light. And that's when Antarctica is going to have 24 hours of dark, right? Same thing happens up here. So if I pick Alaska, for example, okay, so if I have my finger on Alaska, it's just kind of always getting light, right? It never can quite escape that light, okay? Because then you'll have parts of the world get 24 hours of light, okay? When we have this angling, and actually you can see that subsolar point. So again, you can see it on the globe here. Right now it's going through China. It's not entirely accurate because I'm holding at a weird angle, right? It's going through India, right? It's going north of the equator. To angle it a little more accurate. Well, you get the idea, right? That white spot is going to be north of the equator now instead, because while the Earth is angled towards the sun, my subsolar point is going to be in the northern hemisphere. This means that when the Earth is pointed towards the sun, the higher energy sun is focused in the north, so the north will experience summer. The bottom hemisphere, the southern hemisphere, right? I shouldn't say bottom because north and south flips. We'll do that in later chapters, right? The southern hemisphere is being farther away from that high energy is going to be winter. Then if we flip it, right? And if my Earth is pointed away from the sun, and now I have my sun focused on the bottom, that subsolar point is here in the bottom. Now my southern hemisphere is going to experience summer, and my northern hemisphere will experience winter. It's all about where is that high quality sun coming in. Again, where your subsolar point is, that declination point really dictates what time of day does it rain? Do you even get rain? Are you going to have lots of lush vegetation? Are you going to have larger animals that can eat all the delicious vegetation, right? It's really going to be, all that energy is coming from here, okay? So for our view, this is staying stationary, and then this is what moves around, and that interaction between how the Earth is moving in relation to the sun is what creates our days, what creates our years, and what creates our seasons. I hope this was helpful. There's, of course, lots more videos on your Canvas page as well. And it's again, we're talking about things moving through space, which is often hard to visualize. So I definitely encourage you to break out some markers and move things around. And that helps you kind of see how things are moving. That might help you in further chapters where we see, oh, there's a reason why there is a desert here versus a rainforest here. Okay, thanks so much. Bye.